Now, let's say that this is an axis, and let's draw a sinusoidal. Let's draw a sinusoidal wave in this way. This is a sinusoidal wave. There is an analog signal. However, in order to conceive or produce a sinusoidal wave, you have to think that sinusoidal wave is nothing but samples, several samples. You have to perceive the sine wave as samples when you are trying to work with such signals through computer. Because computer cannot process such analog signals, you have to conceive it as a digital signal. Now, this we called one cycle of a sine wave. This is known as one cycle. Okay? This is known as the amplitude. This is the amplitude of the signal. Let's say it is represented by A. The time period, one cycle time period, is commonly known as capital T, okay, which is inversely proportional to the frequency of the signal. So let's assume that the signal has got a frequency which is given by F. Let us say that frequency is F, and let us say the frequency is 50 Hz. Capital T, or the period, is given by 1 divided by F. Is given by 1 divided by F. So this time period over here, this is also known as T. Okay. Now, each of this small parts. So now, in order to produce the sinusoidal signal, you have to produce the sinusoidal signal at each of this point. At each of these points. Okay. These are known as samples. Now, if you look very carefully, in this time period T, there is only one cycle of sinusoidal signal. However, many such sample appears within that time, because as many number of samples we take, the signal will be represented that correctly. So, the frequency with which you sample a signal is also known as a sampling frequency. We represented it generally with Fs. So, let's say that the signal has a sampling frequency Fs. There is a theorem called Nyquist rate. So Nyquist has stated that sampling rate minimum should be at least twice the message frequency. So sampling rate should be at least 100 Hz over here. The higher you take, the better. So let's say that Fs is at least 100 times more than F. Okay. That is okay. So this time period between the two samples is known as Ts. This time period is known as Ts, and Ts is 1 divided by Fs. Now, how you can generate a sinusoidal signal? You can generate a sinusoidal signal by taking the sine value at each of these instances, each of the sample instances. So, we require this timing value. Let's say this is T1, the next circle is T2, T3, T4, T5. So, we have to generate all the T's, and then we have to get the amplitude of the signal, and then if we represent the amplitude, we get a sinusoidal signal. Now, you can see that if this starting period, this one over here, this point, if this point is 0, then this point is obviously capital T seconds, right? So, how do you generate a sinusoidal signal? You can generate a sinusoidal signal by producing a sinusoidal amplitude between 0 to capital T in the steps of capital Ts, right? Suppose capital Ts, whatever the capital Ts value, this is going to be the first one. Then next, after again capital Ts time period, take another sample. Again after capital Ts, take another sample. Now, what if I want to draw more number of cycles? So suppose you want to draw 2 cycles. Then you have to generate the signal from 0 to those many number of cycles into T. So here in the first place, we had drawn the signal from time interval of 0 to capital T. If we want 2 cycles, then we have to draw the signal between time interval 0 to 2t. If 3 cycles, 3t, and so and so. So in simple term, a sinusoidal signal can be generated by this formula. Let's say x is equal to a into sine 2 into pi into f into t, where t is between 0 to number of desired cycle into ts in the steps of ts steps, okay, capital T in the steps of. So we can define t as an interval which is starting from 0 in the steps of capital Ts up to t into number of cycles, right? So according to this formula, let us first model a Python script to generate the sinusoidal signal. Let's go to IPython notebook. Let us declare a variable a is equal to 1. So suppose, for example, the amplitude of the sinusoidal signal is 1 volt. Followed by, let us declare f is equal to 50. Our f is 50 hertz. Capital T is equal to obviously 1 divided by f, as we have discussed. Then let us declare a sampling frequency fs. Let us say it is 100 times that of f. Then we need to calculate those small sampling time period. So let us say Ts is equal to 1 divided by fs. Now, let us assume that number of cycle is 5. That is, I want to develop 5 cycles of sinusoidal wave. So, cycles is equal to 5. Now, sine wave is given by x is equal to a into sine 2 into pi into f into t. However, if you see, we have not yet declared the small t. We have the capital T, we have capital Ts, but we don't have small t. If you go back over here in your program, you can see that the small t has to be developed. We have already studied that in Python, by taking the range command, you can create a numeric value. So if you write a is equal to range 0, 10, 2, it is going to produce numbers between 0 to 10 in the steps of 2. That is 0, 2, 4, 6, 8. However, range doesn't produce float numbers. Okay. So if you want to produce float numbers, you can use the command called arange. Okay. It is not arrange, this is actually arange. A stands for actual numbers. So now you can write 0.2. So you will have a number with 0, 0.2, 0.4, 0.6, 0.8, 1, 1.2, 1.4, 1.6 and so on. So we had already worked with range command, and we have seen that a is equal to range 0, 10, 2 will produce numbers between 0 to 10 in the steps of 2. However, the range doesn't produce real numbers or the float numbers. Okay? Now, as for our discussion over here, obviously the value of T, the value of capital T, they are all going to be in float numbers, right? So therefore, what we do is we import so what we are going to do is we are going to import Numpy. A range is actual range where we can actually produce a number, okay, in a real number. So 0 to 10 in the steps of 0.2 will give us the number between 0, 0.2, 0.4, 0.6, 0.8, so and so, so and so. Okay. Now we are going to use a service because sinusoidal signal drawing is not enough. We need to also visualize it. For visualizing, we'll be using Matplotlib. Many a number of times with the web page notebooks, such things do not run. So in order for you to be able to run that, you have to add one extra command, %matplotlib inline or %matplotlib notebook. Instead of inline, you can also give notebook. Okay. Now import the matplotlib. Okay. And if we say np.plt.plot np.array 1, 2, 3, 4, it is going to show you an array. Instead of this, now I want to create a sinusoidal signal. Remember that sinusoidal, let me take a new cell for the sinusoidal signal. Let us take a new cell. You can click on the new cell icon from here. So now, let's say a is equal to 2, f is equal to 50.0. Now, you see, if you declare f is equal to 50, what will happen is, when you are trying to calculate p is equal to 1 by f, if you declare f is equal to only 50, right? If you declare f is equal to only 50, it is going to consider that to be just an integer number because there is no explicit data type declaration. So t is equal to 1 by f will become 0 because integer number 1 divided by 50 is obviously 0. In order to avoid that, whenever you declare the variables, declare it in float fashion such that even your t is float. Similarly, let us say fs is equal to at least, say let's say 1000 times that of f. And similarly, ts, or you can also take it 1000.0 times that of f, and ts is equal to 1 divided by fs. ts is the sampling time. Let's say number of cycles equal to 3. I want to plot a sinusoidal signal with 3 cycles. So now x is given by a into np dot sine. We have already imported Numpy as np. So np dot sine 2 into pi. Pi is also present in np package. np dot pi into f into t. Now you see, we have not found out the variable t. In order for you to find out the variable t, t is equal to np dot a range. We have seen how a range can produce the numbers, okay, the real number. np dot a range 0 up to number of cycles into t. T number of cycles you want to represent in the steps of ts. Okay. So let's execute up to this, and you can finally plot this by using plt, which is nothing but matplotlib.pyplot, plt dot plot x and plt dot show. So I can copy this if in case this cell doesn't work, you can take a new cell and you can work with this. Okay. Let's restart the kernel. Now let's copy it and let's create it. Let's close all the kernels which are there. iPhone 3. It shows that the kernel is ready, so let's paste the entire code that we have developed and let's run this. ARANGE and instead of inline, let us take notebook. Let us run cells. Okay, so we get 3 cycles of sinusoidal signal. What if I make it 10 cycles? Instead of 3, what if I make it 10 cycles? Cell, run cells. You are not going to get 10 cycles of there's a problem there. So I'm going to put this first off. So 10 cycles of sinusoidal signal. What if I do not take fs to be this bigger? Just if I take fs to be only 2 times the f, if I make fs only the 2 times of f, what will happen? Cell, run cells. You see, it will look something like this. As I keep on increasing fs, let's say at least 5 times or 6 times, you will have several number of cycles. Cells, run cell. Now you get a sinusoidal signal, but it is not going to be complete because it have this top product, and as I keep on increasing the sampling frequency, so if I make it 16, the cell is going to be much more clear, but still you have some noises. As you keep on increasing this sampling frequency, the sinusoidal signal starts getting much more clearer. There is one more plot which is known as the Sine plot. Let me show you by reducing number of samples to 6. So Sine will represent every independent value and number of cycles. Let me take just 1 cycle. Okay. So if you take sampling frequency to be 6, these are the 6 points where it is going to be sampled. Okay. As the sampling frequency is changed to say 16, you'll have much more number of samples which is going to represent the signal. But you still have an approximation over here. As you keep on increasing the sampling rate, say make it 50. Now you'll have, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. You had totally 16 samples. Now if I make it 50, you'll have 50 samples, okay, with these number of errors. And if I make it 500, the digital signal if I make it 500, the digital signal itself will look like the analog signal because there will be too many number of samples. So no worries. Let me start one more time. Then click on cell, run cells. This absolutely looks like an analog signal because we have taken too many number of samples. Again, if you reduce the number of samples, make it 10, you'll be able to see how exactly the sinusoidal signal is going to proceed. So this is how we can create a signal, and in next class we will see how the signal processing is performed.